All right. So the average is 78, right? Which means that difficulty is quite okay. Because 70, because this is a research graduate course, right? So 70 should be the, the lowest score that you can pass this course. So 78 is about right. Okay. So you can imagine that what kind of percentage you are in this course. So this is the first thing I want to announce. The second important thing I should announce is that I noticed that we only have 2 physical interaction between you and me. Only 2 times. After today. Okay. Next week, I need to interview admission of the master degree students. Okay, next week. So I cannot physically present here. So I will upload my video and I will ask you to finish that by then. And then, accidentally, next week will be the sport event of campus. So the calendar said no course for that day, but we could do that. We could do lecture. Do you want that? How about that? So I can vote. Okay. 20 of November will be the sport event day of the campus. Calendar said no course but I can do that. All right. So if we can vote, either you want to see the video or see me here, we can both do that. All right. So I can vote on the Facebook. All right. So you can vote, and then if more students would like to see the video, I just publish the video. Okay. If you want me to see me present here, I will do that too. Okay. So next week I cannot have a lecture. I'm sorry. I need to upload the video. And next week I can do the vote. All right. So that's it. And then suppose our next midterm too is the range will be 4, 5, 7 PDF. Sorry, 4, 5, 6 PDF. So suppose, well, we can immediately have our final midterm 2 on 27th of November. Okay, 27th of November. Yeah, but we can adjust. Yeah. So suppose 27th of November we'll have our midterm 2. So we can, if 20th of November you vote as a video upload, and I won't see you after today until December. So everything is so coincident in this semester. Quite annoying because I guess this is because typhoon holidays, I guess. And also, yeah, and then only 2 weeks in December we can have physical interaction of the lecture. So 16 weeks, a little bit short for this course, but I will try to make it in time. All right， 听懂我在讲什么吗？下礼拜我要去口试硕士，所以我真的没办法，因为我是招生组组长，所以我必须要去做这件事。那我就会 upload 我的去年的影片，但是下礼拜是运动会，它上面行事历写说停课，但实际上我是可以参加的，我是可以上课的。那其实很久以前，大概5年前以前是硕博士班是没有停课的。那但是行事历是写大学部停课，但是 at some point 就变成 全校停课。所以在5年前的时候，我是照常上课的。那现在的话，我们就可以投个票，大家觉得说要我上传影片呢，还是我要照常上课，我都没有问题哦，我就投票让大家就是看看是要遵守学校的 calendar，还是就是我还是来上课，这都是没有问题，对我来讲是还好。那接下来呢就是期中考的第2次了，第2次的范围是4、5、6的 PDF，OK，所以理论上来讲，下礼拜应该就会讲完了嘛，我猜了哈，理论上。那所以27吧，就是11月的20几号的那个礼拜3，可以是期中考第2次。那当然了，我们可以做正式决定，如果今天有任何的问题啊或者什么都可以先跟我反映。那接下来就是12月了，12月的话也只剩2周，我们可以见面，然后就要期中考了。所以16周对我们来讲其实有点赶，但是我们就尽量靠 video upload 这件事情来就是帮助我们，让它就是可以 OK 这样子。好，那听得懂哈？然后平均78分，然后70分就不及格嘛，所以78分我觉得还行了哈，难度调整还算 OK。好，那大家对表现不错，好，谢谢大家。那如果有任何问题，就赶快等下可以告诉我，或者是对，或是私讯我也可以，email 我也可以。All right. So if you have any questions, just email me or message me. Well, in case Facebook won't or other stuff, other thing, won't reach me, something like stranger message won't reach me. So I don't know. Maybe just email because we are not friend in Facebook, right? Or IG something. Anyway. Right, so let's continue. So last time we talked about thermodynamic probability, which is not real probability. It's a number, okay? The number. And the number can make it as a real true probability, like this. Yeah. True probability, okay? True probability divided by all the possible occupation number. All right, and then you can do the expected value to have the results, and then we have binomial coefficient, which we are quite familiar with that because we learned that in senior high school, right? And then we talk about 4 coins and 8 coins, and then 1,000 coins, and then you notice that the peak is quite a really big number, okay? And then we also introduce the Stirring approximation, which we will use that quite frequently later on, all right? And then we found that this is a really big number, even with 1,000 coins. So you can imagine that in a real system, we have large number of atoms, large number of coins. You can imagine that. And each coins only have 2 states, but atoms may have many states. So you can imagine that how big of the possibility it is. So you can see that N1 equal to N2 is the one that almost always occurs. Always occurs. Okay? So you can imagine that the system, the material that you see in the real world will always be the most probable states that you can see. Okay. Right, so let's continue. Most probable configuration. So you see that this is older the region. What does that mean? This is if this is a head, tail, or head, tail, head. So this is kind of older. You see, this is really older, and this is maybe tail, head, tail. So it's really older the region, but here almost really random head, tail, head, tail. So it's kind of old random region. So the older region almost never occurred. And you can imagine that all the possibility is actually really similar to W mix when the number of coins become greater and greater. So you see, this is really small possibility, and this is so high. So it's almost can be neglected. Okay, so W max occurs at the peak, where of course this the slope is has zero slope. So you can have an extremal value for that. Right. So this is when m is big. Okay. So I guess you can understand this. And then for binomial problem, n has n1, n2, head and tail of the coin. But now moleculars may have more results, as we mentioned, n1, n2. Previous coin only have n1, n2, head and tail. But now, it's many states, so it becomes w equal to n factorial, n1 factorial, n2 factorial, n should be factorial, right? So that's it. And it could be rewritten in a more concise form by using this symbol. Okay, m factorial divided by, well, I don't know how to pronounce this, but it looks like pi, like sigma. So you can see that sigma means plus, right? But pi means multiply. Okay, so just introducing a symbol that help you to make it more simplified, concise present illustration for your equations. So molecular in the gas, the particles are normally identical and indistinguishable. Why it looks like this? You should go here. Okay, molecular in a crystalline. Right. So in gas, atoms flying around, so you cannot tell their differences. But in solid, typically they have particular structure, so you can identify each atoms by its neighbor, right? So yeah, so everything becomes distinguishable in the solid because the location, the position of the coordinates and system coordinates. So you can understand that gas is more or less identical, treat them as identical indistinguishable atoms, but solid may treat as a distinguishable atoms. 好，那就讲这个，上次有讲过了哈，就是几乎在刚刚讲的正反这种东西，如果这边的话，几乎大部分都是正，然后一点点反，所以它其实是非常有秩序的。那这边就是反过来啦，哈，全部都是反正反，所以说它是很有秩序的状态。但通常这种是正反正反的这种东西，非常的不随机的，那就是最有机会出现在我们生活中的。OK， 而且这个机会，如果 n 很大的时候，数量很大的时候，基本上这些是可以忽略的，所以全部的加总几乎就等于 W max 了啦。那 W max 的话要怎么找到呢？就找斜率为0的就好了。好，那我们刚刚讲到 硬币就只有2个状态，但是其实上有非常非常多种其他的状态在真实生活中 atom。那所以我们要做的话，其实就是把N1 fertile N2 fertile 加弄到最后面就对了。OK，然后我们把它解成这样子比较简单。这个东西其实就是我们的乘的 sigma 了，哦，是乘的 sigma，sigma 是加嘛，派就是乘，连乘就对了。那这边有个蛮好的概念，就是气体的 atom 就是在瓶子里面飞来飞去，飞来飞去嘛。那所以你基本上是无法得知说，哎，这个跟那个无法分辨。但如果是固体的话，那它就会有晶格排列。那晶格排列的话，它就会知道哦，旁边是邻居是谁，你就可以判断现在你在看的是哪一颗。所以说，实际上它是可以被分辨的。OK， right. So let's continue a more material-wise, but still a toy model. This is still toy model. Okay. So let's take a look. Distinguishable particle. So there are a system that has undistinguishable particle. Okay, occupying a fixed volume V. You can imagine this is a container. In an isolated system, the macro state in the system is defined by, okay, so you can see that this system defined by N, oh, sorry, N and V and U because the isolated system. So NVU controlled by human, controlled by experimentist. All right, just like you. So this is a system that controlled by NVU, or sometimes we call NVE energy. Okay, so see that NJJ again, this is an energy level. All right, so from the first energy level to the end of the energy level, summing up together become total number of particle. It's called conservation of particle or conservation of mass. And the energy Nj times epsilon J is the energy of that energy level, and times its the number occupied that energy level. Summing up together, of course, it becomes internal energy. Okay, conservation of energy. So you need to satisfy this two fundamental equation when you discuss NVU system. Okay, so for example, if you only have 3 particles in the box or container, and energy you fix that the total energy is 3 epsilon. For example, just heat it into the certain temperature and make sure that the energy stay the same, okay, and won't exchange to the surrounding. And then you make sure that this is 3 epsilon. All right. So which means that what kind of states that you can get in this system. So let's list all the possibility. But you see that this is 3 epsilon and 3 particle. This is just toy model that we can make calculation by hand. But real world will be different. But this is just in practice. All right. So so the energy level is so let's take a look. So you have such energy states of that 0 epsilon, 2 epsilon, 3 epsilon. And of course, the 0 epsilon, 0 is ground state, which means that the particle has occupying a ground state that no energy at that. So you can imagine that the total you need to be 3 epsilon. So how many possibility you can have? So you can see A, B, C particle, A, B, C particle, will has either C become 3 epsilon, 0, 0 of the remaining particles, or B become 3E, A become 3E. Okay, so you only have 3 possibility, thermodynamic probability. All right, and or you can have all the particle A, B, C has epsilon, epsilon, epsilon become 3 epsilon, of course. So you only have 1 thermodynamic probability. Or you can have one of it become 0, but the other has epsilon. The other has 2 epsilon. So sum up as 3 epsilon. Okay, so you see either A 0 epsilon 2 epsilon for B and C respectively, or 0 for A, 2 epsilon for B, epsilon for C. So you can list all the possibility, and then you can see that 6 thermodynamic probability, and then you see the true probability is 0.3, 0.6, 0.1. So you see that this is the most disordered region, right? Older. The most disordered for this. And then you can see that this is the highest probability for this. Okay, and also, yeah, that's it. 好，讲中就是刚刚是叫什么？硬币现在又变成一个玩具的模型哦，玩具模型就是3颗假设啦哈，原子。那应该这样讲，我们先从 general 来说，就是理论上来讲，一个瓶子里面有很多particle， 然后那有 n 个，然后它在一个瓶子里面 v， 那它是 isolating， 所以能量固定的，所以我们是用 NVU 是我们人类决定的，我们可以决定它是什么样的状态，然后它会是什么样的情况呢？它有几种情况会出现在这个状态里面呢？那我们必须要去满足这个东西，就是全部的能阶加总起来会是 n， 然后全部能阶的颗粒乘上它自己能阶的能量的话，要是内能总和。好，那这样子这是定律嘛？那理论就是一个例子，就是说我们只有3颗，然后它的 U 是3 epsilon 的话，然后每一个 energy level 从0，第一个 energy level 是0，第二个 energy 是 epsilon， 第三个 energy 是2 epsilon， 第三个是3 epsilon， 第四个了，第四个是 epsilon， 3 epsilon。好，总之就是这样弄上去，所以一颗有可能是这几个能量。但是你总能是这个，你不能超过嘛，所以你就把这边列出所有的东西，你就会发现中间这个是最有机会的。所以如果今天你控制你的刚刚这个瓶子是这样子的状态的话，你去看它一下，通常你都会发现它是这样子的状态，都是在处于这种状态，一个是站在最底下，一个是站在第2个，一个站在第3个这样子的状态。OK， 那如果今天你是更多的话，更多原子的话，那就几乎100%，然后你就看到这里都是在 the most disorder 的位置，最随机的、最没有规律的位置，会找到你会找到你现实生活中的状态。Okay, so let's introduce ensemble. Ensemble is quite important concepts, especially for simulation or theoretical calculation of the material science and engineering. All right, let's talk about it. Ensemble is that the relative magnitude of the fluctuation is inversely proportional to the number of molecules in the system. Oh, okay. Okay, so let's talk about how can you say your experiment measurement is accurate? How can you say that? How can you make sure your major result is accurate, 100% accurate? We cannot, right? We cannot do that because we always introduce error. But what the best we can do? Let's take a look. So there is a pressure measurement for this particle, for this container gas. The particle will hit the wall and then generating the pressure that you can measure, right? So imagine that there are 3 particles in a container, and you can imagine that when the particle don't hit the wall, you will measure 0 pressure, right? But if all the particles sunk at the same time, when you measure that it hit the wall simultaneous, it will become higher, right? So you can imagine that when you measure this pressure, you can measure something like this, up and down, up and down, up and down. So what is the pressure it is? The real pressure, so you can see Pi, which means that you can measure many, many times. Okay, P1 times P2, P3, P4, P5. So what is the real actual pressure you can define? PLTA, long time average pressure. So you average all the value of your measurement. So you can have the PLTA, long time measurement average will be the most accurate, most reasonable result that you can give us 100%, right? Nothing can be better than this for a human being, right? So that's the ideal things that we want to say. This is the best, but we cannot do that, right? We cannot measure them long time. So in our mind, that we can do that is doing the ensemble. What is ensemble? It's a mental collection of a large number of the system with the same properties. Okay, so you imagine that you have the 3 particle container like this, and you in mind you copy that a lot of the member of this, and they are all the same, has 3 particles with the same kind of energy, and then you measure them once, so you can say in some ensemble member number, the first member you get this one, the second member you get this one, the third member you get this, all the member, and then you can have the P bar. Okay, so we will say the ensemble average P approximately equal to PLTA. So you can imagine that you need to measure long time, but now you have group of people and then you measure once and then average them. So you can see that this and that should be similar, right? So previous few years, my next page was Naruto. You know that Naruto has the very famous skill that it can multiply himself, right? And if you know the story that he multiplied himself to train himself to save time. Do you remember that story? I don't know because it's too old for you, maybe. So because 5 years ago I had that page, but at some point students don't understand what is Naruto. So okay, I deleted that, but I still introduce this story. If you understand that, I think they can help you to understand ensemble. All right. 好，就这样。Ensemble 就是一个叫系中，系中呢就是你要我们要我们在讲解系中之前，我们要先讲一下，就是说我们要怎么样量测最准的实验值呢？我们使用的是要量好久，量好多次，然后把它平均起来。那这当然了，这是一个哲学啦，这是一个哲学。就理论上来讲，你要量 pressure 的话，压力的话，你这个3颗有的时候撞到，有时候没撞到墙啊。那有时候1颗撞到墙，2个撞到墙，有时候3个撞到墙，所以你的压力理论上呢会是起起伏伏的。那我们量到的话， 我们就是要平均它，但这是不可能的事情，所以我们就用心中去想象，就是说我们有很多个这个同样的东西，那它们有不同的状态，因为它们同样的状态，但是它在不同的，就是你有复制它很多复制人的对，复制系统，然后同时去量测它。量测完以后，全部平均以后，我们就会发现这个图跟这个图其实非常非常类似的，只是一个是用时间换去量测同一个，或是一个是用复制的，就以人的量来取胜就对了。你只要瞬间量完一次以后，你就可以得到约等于 long time average pressure。那我刚刚讲到，就其实之前的下一页都我之前是放漩涡鸣人，当然我不知道大家现在还认不认识他火影忍者，因为他会他会引分身嘛，所以里面有个故事情节，就是他为了争取时间，所以他就是把自己变成很多引分身，然后一起做训练嘛，对不对？我不知道大家记不记得这一段，那或者说是有没有听过这一段？那这就是有点像是这样的。原本一个人你要练很久，但是他现在是很多个自己，然后练一次，哎就可以达到很好的效果，就这种感觉了哈。好，那这玩意干嘛呢？其实就是说啊哈，以后尤其是对做材料计算模拟的人就很 OK 哈，就是其实你可以分子动力学很多次啊，然后很多次，或者是你跑很多步，同样的状态很多步，然后但是每一步都不一样啊，因为他们都有自己的随机性，对不对？那你就把它平均起来，你就知道它最后的答案是多少。所以我们常常会用分子动力学说，哎，你是用什么 ensemble 去跑的？NVT 还是 NVE 什么？这时候我希望大家就听到这个ensemble 是什么东西啊，以后你可以跟模拟的人聊天的。哎，OK，next。So type of ensemble. Ensemble is micro-canonical ensemble or canonical ensemble and grand canonical ensemble. But, well, I don't know why the name is so interesting, but the definition is easy. So you define the system as NVU, which means that you fix number, volume, and energy. And then we introduced that previously, right? So also known as NVE. All right. And if you choose to fix NVT, you fix temperature. It's called canonical ensemble, a closed isothermal system. Well, you notice that this is easier for human being, right? You can control the mass, volume, and temperature. That's easier for us, right? So this is what we always focus on. And ground canonical ensemble is mu VT, so which means that you constant nu, but you will change the n. It's an open isothermal system. And then we have some assumption that all the quantum state, which means that you can the particle can access that, can occupy that energy level. So quantum mechanical allowed, okay? And yeah, long time average is equal to the ensemble average. Okay, so that's I introduced that in the previous few page. 中文讲完就是有三种可能，三种系中我们常讲的。第一个就是控制数量、体积、能量。第二种就是数量、体积跟温度。你可以发现这个是很好控制，对人类来讲，所以这是我们常做到的。然后接下来是 constant new， 那是叫 grand canonical ensemble， 那就是比较难的哈，它会 open， 它会改变它的那叫什么质量。然后这边就是接下来假设就是说，大家都是每个能阶都是不会有 preference， 不会有喜好的，他们都公平的去选那些东西。然后最后一个就是前面那页讲的长的时间的平均会跟气中的平均是接近的。好，那 sorry I late for 2 minutes, so I will see you after 20 minutes. 22. Sorry. 12 past 10. I will see you 12 past 10. Thank you. Bye bye. 有问题请找助教。然后为了改分的公平，因为他们是改的，所以不要来问我。谢谢。
这边用的是这个6月份。但是其实它基本其实完全比较高，所以它其实主要的话，它的后期的经历，这样子的话就变成前这种情况，而且这就看前面的。好，但我也觉得就是 而且他也上过要求用每种机上面啊，教这些都有大陆统一这样会转变成一个之类的，就看有
就是像这一题嘛，然后他这边前面提到 NID 不要死这样，然后他最后算的结果之后，他会算乘上就是原子个数的这样。有同学说，因为他前面看到他都按 NID 个，所以他把它当做这一课的，所以他就没有把它乘上万这样。他是这样可不可以这样？因为有的人他把它当成这一课，所以就没有乘上万，他当做他这一课这样。
没有，如果是 an ideal，如果是这样的话，应该是 an ideal diameter gas atom。对，那当然不用全错了，你只扣一点点就好了。你有扣一点点吗？我不知道，我不知道。
没有，因为那时候我看他错，我以为就一定要乘，我就把它这个扣变了，扣1.5的，
1.5，
因为
OK 啊，
因为他其实他主要是有算到，就是没有每一个都有干涉到的。
1.5就好了，对，就是扣一点点就好，当然不是全错，
对，不是，
对啊，很好，那都很好，我觉得是对的，你的，我支持你，对。
这个是对的。谢谢。
Okay, welcome back. So let's continue. So type of ensembles, sorry, the micromechanical ensemble is that we just talked about that in the previous few pages, right? We have the example NVU, right? The 3 atoms case, the toy model. It is an isolated system, fixed NVU, and the probability Pi of any given state is Pi equal to 1 over omega. So you can imagine what does that mean? It means that all the states has equal possibility. So you remember that we list all the possibility and then we calculate the true probability, right? So each of the energy levels for them are equally preferenced. Okay, equally preferenced, preferred. Okay, so no preference for one of them. So they are all equal possibility. Okay, so this is this means what we said, what I said. Okay, so and also this omega is defined by MVU, defined by human, right? Remember that this one, your omega, sum and not together. How many? This is defined by the MVU, right? The defined by us. If this is 6, oh, everything changed, right? So changes. So yeah, that's it. So and also we said that our assumption is that all the system, I mean this sorry, this basically reflects this postulate assumption. Actually, they are the same. Okay, this is mathematical expression. This is an expression by text, by human language. Okay, and then ensemble average pressure will be the expected value. All right. Okay. Sorry, it should be, yeah, P at P bar equal to, yeah, something like this. And their E bar equal to 1 over omega. Summing up all the EI. So you can get E. So you can see that this is the statistical way for us to obtain the macroscopic, the large scale properties. This is large scale property that we measure in the real world. But in the small scale, we do this. We make it the value with the probability. Okay. So for example, in page 12, that's what we do. Oh, okay, that's what we do. 12. We just swipe back to the page 12, right? So microeconomic ensemble, we mentioned this before. 好，我们其实刚刚在第12页讲那个3颗的那个玩具模型，就是在讲这个。好，那 NVU 这个东西，那我们它的所有的 given state 都是它的 pi 好就等于是 omega 分之一，什么意思 ？omega 就是全部加总起来嘛，那分之一就是它其中的一种。这样你可以看得出来，就是其实每一个能阶的状态都是同样的几率，好，选择权都是一样的，选择都是一样的。那这一句话其实就是用用英文讲就是这一句话了，哦，那用数学讲就是用这句话。那这两个其实是一模一样的，就是一模一样的意思。那有了这个以后呢，我们就把如果是 pressure 的话，那我们就可以得到，就全部加总起来，然后就可以得到它的 pressure。那我看一下哦，不好意思，我这边要讲一下，sorry, I should make it this P is not equal to this. Sorry. This. Let me rewrite it again. Sorry for that. This is probability. This is small p, and this is capital P. I'm really sorry, I forgot to mention this. So this is different. All right, this is different. Okay, I'm sorry. This is probability P, and this is pressure P. I'm sorry. 啊，重讲一遍，就是这是几率啦，哈，每一个能接的几率。但是呢，接下来就是如果我们就要讨论的是平均的ensemble average 的话，其实就是把每一个状态的 pressure 平均起来就对了。好，这就是平均起来，平均起来以后就得到巨观的 P， 每一个状态的能量平均起来就得到它的能量。所以实际上基本上就这样了哈。Okay, ensemble. Again, this is the canonical ensemble is actually the more common for us because it can control N, V, T. T is better for us to control. So let's imagine that there still has we have two particles, blue and green, and each of them has three position momentum coordinates 1, 2, and 3. You can imagine that they have the momentum, okay, level 1, level 2, level 3, something like that. Okay, so in a closed system, energy is interchangeable with the surrounding, so it can be exchanged, but the temperature is the same. All right, so you can imagine that it's a big water tank surrounded by the system. And also, let's take a look. So this two particles, the two particles, it's called MVT. MVT ensemble, and then you can see that green or blue particles has 1 or 2 or 3 states. So you can list all the possible quantum states in that in this situation. So you see, it can be either 1, 1, either 1, 2, or 2, 1. This is actually blue is 1, green is 2. This states blue is 2, green is 1. Okay, so they are different, but the energy level is the same because they have the same energy summed up together. But in each, when you see that focus set, you find that actually they are different. So this you can see that this degeneracy is 2. All right, and next level 2, 2. All right, only one energy level, 1 degeneracy. 1, 3, 3, 1, 2 degeneracy, and 1 energy level. 2, 3, 3, 2, 2 degeneracy, 1 level. 3, 3, 1 level. All right, so this degeneracy can be seen that by a quantum states difference. Okay, so again, this is really important. Now, so you imagine that you have many systems in the water cooler. Okay, and you see, member A, ensemble member A is 1, 1. Okay. Ensemble member B is 2, 3. Okay. 3, 1, 1, 2, 1, 3, blah, 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 blah. All right. So this is time T. How about if you measure next time? A become 2, 2. Oh, they are different. B is 2, 3. Oh, they are the same. C is 1, 1 or 3, 1. Not the same. Okay, so you can see that each member at different time are different, but the distribution of the entire ensemble member are the same. You can see, for example, 1, 1, 1, 1. Although the 1, 1 is different, but it becomes C and K, but overall, they are all the same. So you see that each of them, for example, EA at T, this has EA at T1. You can see that EA at T, EA at T1 are different, but the distribution of the ensemble members not change. Okay, the distribution over the allowed states has not changed. Okay, so which means that for the ensemble average method, actually time, the time T plan has nothing to do with the distribution of energy, or you can say ensemble average energy. So the ensemble average energy is, I should write it down, is small p, right? And EI. So the probability of it times its energy, and summing it together, you can have the ensemble average energy. OK， 好，我们先开始讲翻译，就是现在来讲比较大家常看到的 canonical ensemble， 它是控制 NVT 对我们人类比较容易啦哈。我们现在想象有2颗，它2颗有一个这种东西，就是它的能量的那种状态有1阶、2阶，第一种状态、第二种状态跟第三种状态。那我们就来看看到底它这样子总共有几种状态，还有同时都是1的话，就一种状态，然后一种 energy。但是2的话，可能会是有一个是2，另外一个不是2啊，是1，所以就是1、2，蓝色1，绿色2，蓝色2，红色1，绿色1。好，所以总之就是他们会有2种状态，但是他们都总合起来都一样，所以有同样的一种 energy level， 所以你可以看到 energy level 这个的 degeneracy 是2。OK， 所以你可以这样子排下去，你就可以发现哦 ，degeneracy 是这样子来的。好，也就是说不同的状态，但是不同的状态都给你同样的 energy 啊。好，那接下来我们就要看我们刚不是说 ensemble average member 什么意思呢 ？ensemble 系中成员，也就是说同样的东西，你就是给它复制引分身数，就把它复制成一大堆，那你可以放在同一个地方啊。那你在T 这个时间点量测的时候，它是11，它是23，它是31，然后这个 EA 啊，这个状态它的状态就是这个状态咯，对不对？它在 T 这个时间你量测到的结果是这样，但是你到下一个 T prime 的结果 A 变了 ，A 变成22这个状态了， 哇，那想说，哎，那这样子可以吗？哎，因为我们不 care 就是引分身数的每一个单个，我们是看整体。好，你看整体，你看这边是一，这边有一啊，对，那换了一个时间点，还是有2个一呀。好，我只是大概跟大家讲一下，就是也就是说，虽然每一个人的能量不一样，但是你的分布能量的整体的几率的分布是完全一样的。所以说，你如果考虑 ensemble average 这个 method 的话，系中平均这个方法的话，你在哪个时间量测，其实答案都是一样的。那也就是说，我们不需要长久的量测就对了，我们是靠人的数量来取胜。OK， 那总之这样子就可以等同于之前的同一个东西量测好久这种状态。那对，那就是这样。所以我们的能量能阶乘它的比例期望值加起来就会是我们平均的能量。Okay, now example 2, more specific, and we want to introduce more stuff, more interesting stuff, and this is the core of statistical thermodynamics. All right, now the very large water cooler, very large, okay, and each of the breed has one bottle, okay. Each bottle has 10 to 12 molecules. Oh, bigger number. In the 330 ml is a volume fixed with the molecule interacting with one another in each bottle. Okay, so you can imagine that there are some particles inside, and then we know from the quantum mechanics that there is an innumerable set of allowed macroscopic energies. So you can imagine that this system can have different energy, okay, different energy from each bottle. But we are going to see how much, how many probability. Okay, so the set of energy can be seen here. Allow the set of energy. So we use a symbol. This means that a group, something together, assembling. Okay, so all the EI, summon, not summon out, just gathering together. All the energy, EI with the bracket is a assembly. Everything set, all the set in this set. Okay, so this is the energy, EI, and this EI defined by N and V. Okay, right. So the key question is that what is the probability that your water bottle, you pick up one bottle, will be in the state I with energy EI? So the question is that you pick up the bottle from the big water cooler. What is the probability that your bottle has EI energy? That's the question. OK， 好，我们现在讲的是 example 2，就是我们有个很大的那个叫什么水域就保持温度不变的东西，然后你的瓶子里面有10的25次方的原子，然后你有330个毫升的体积。那现在我们每一个，就是你可以想象，它其实这个瓶子可能可以有很多能量种类，能量的分布，不应该说每一个瓶子都可能有不同的能量哦，都可能有不同的能量。那它的能量的总和就是就是你可以把它写成一个符号了就是把它写成一个集合。对了 ，OK， 这个集合里面，我从里面挑出一个瓶子。那我们想要问的是，你挑出来这个瓶子，有可能是 EI 这个能量的几率是多少？可能你会你如果用巨观的想法来看，就是说，我不是给你 NVT 的吗？我拿出来都是应该几乎都是同样的能量吧？ 那是结果。就是说，你几乎拿出来的都是你看得到的能量。但是我们不要想这个，我们要想是说，它其实有可能是别的能量啊，只是我们没拿到而已。所以我们必须要想的是这样子。所以我们要说，我们要算看几率，就是说就是你拿到 EI 这个能量的几率是多少？搞不好很低啊，你永远拿不到啊。但是它还是可以被算出来，这样的意思。Okay, so let's continue. So number of states, we will use AI to indicate the number of bottles. So a lot of bottles, right? And there are AI bottles has energy EI. Okay. If your energy is EJ, your number of bottle is AJ. Okay. So the ratio of the number of bottles in states J and K will be AJ over AK. Yeah, so if you are going to compare how many bottles in energy level EJ and energy level EK, a number of bottle is AJ over AK. Of course, it must be a function of EJ and EK. No problem. So this function, definitely no problem. All right. Now, important. This ratio should not depend on the arbitrary choice of 0 for E. What does that mean? Let's take a look. So your energy level, EJ, and this is the energy level. I should make it a level. It's a level, EJ, and this is a level, EK. Sorry, I will make it upper. Okay. And we know that there are AJ bottles for this. We have AK bottle for EK. Okay. So now the question is that actually the energy level is relative. It's relative. Okay. Because the energy, 0-point energy can be defined by human. Your energy level, ground state, E0, actually can be here, or can be here, or can be here, or can be here. Okay, so basically the origin of the energy, 0, defined by human. So the something really important is that the difference between the EJ and EK. Okay, so if you can accept this, the AJ and AK, yeah, it's function of EJ and EK, but can we introduce more physical insight of this? EJ minus EK. Actually, the difference matters. All right. Consider another system having energy EL. So the ratio of AJ and AL is FEJ minus EL. So you can see that ancient scientists, ancient smart scientists, they try to solve problem by introducing what they observe in the real world. So for example, this is correct, but if they cannot go down to this, if they don't find, actually the origin is defined by human. If they cannot do that, we cannot proceed the proof, discover the new stuff later. Okay, so this is quite extraordinary. They are really smart. Yeah. All right. So AJ over AL is EJ minus EL's function. aka K and L, EK and EL. Okay, no problem. And then next page, we will use this one to explain something. 好，我们要讲的就是开始了。刚刚不是说要把 auto 拿出来吗？拿出来，你拿到的是 EI 这个能量的几率是多少？我们想要知道这件事情。那我们现在就来看啊，如果今天你有 EI，你拿到这个大的除频器，我不知道怎么讲，反正就这个大冰箱哈，这个大冰箱里面有 AI 个 EI 的能量瓶，有点绕口。如果你今天是拿到 EJ 的能量的话，你有 AJ 个能量的瓶子里面有 EJ 的能量，这样好不好？那它的比例 AJ 个除以分之 AK 个，不对 ，AK 分之 AJ 个，它其实这个比例其实就是 EJ 跟 EK 的函式嘛，一定的嘛，就是 EJ 是多少 ，EK 是多少，就可以去找它的数字瓶子，然后它比例就是这样，所以它的这绝对是没有问题的。但是聪明的古代的先知先贤们，他们就很聪明，就是发现，哎，其实能量差才是重点，因为这个 EJ、EK 这个数字是人类去定的，那原点在哪里？我们都可以随便定啊，哈。所以说，刚刚有在那边画来画去啊，哈，这10个可以在这里，可以在这里。那所以其实真正来说是能量差才是最重要的，所以我们就把这个东西写成 EJ 减 EK， 它当然是这样子的函式，但是实际上更先知先贤这么聪明，他把东西就是更重点把它写进去了，这才是重点啊，差才是重点。好，把它写完，如果你觉得 OK 的话，我们就把 JL 减 KL 减这样子 ，OK。好，那如果这个东西可以的话，就接下来就可以，你可以看到他们使用他观察到的现象，然后就可以帮助我们去得到更多的资讯。OK，so now AJ over AL, if you see the value AJ over AK, AK over AL, you can cancel each other, so you can get AJ over AL. And the AJ over AL, so you can see this is multiplication, right? F EJ minus EK, F EK minus EL. And this one can be written EJ minus EL. Of course, this is definition, right? But this definition equal to this one. Oh, so you can notice that the function has some behavior that x plus y, and this is x, and this is y. Okay? So you notice that the function, if the function x plus y equal to fx times fy, oh, it must look like a exponential. Okay? So you know that y exponential and natural log co-nature because a lot of physical behavior follow this function, exponential, EI. Okay? So AI must be looks like a exponential because x plus y, the function of x plus y equal to fx times fy. Okay, so it must be a exponential power value. Okay, so now of course this is equal sign, so we definitely need a coefficient in front of it, and of course we can have a coefficient beta. But is that okay? Well, a little bit weird. Exponential looks like. The exponential looks like this, right? So which means that if you have a higher energy, you will have infinity bottle number. That's not good, right? That's not right. So it shouldn't be positive. It needs to be negative. Okay. Although it looks like a exponential, yes, but the coefficient need to be, need to be considered. So it doesn't fit the real world. If you have x greater than, x greater and greater, and you have more, you have infinity bottles, that's not right, right? If you have infinity energy, you should have really, really little chance to get that, right? So actually, you need to be opposite way to do that. So that's the reason why you got, if you have the minus sign here, everything makes sense, right? So this that we need to make it minus beta. OK, that's it. 好，我们刚刚讲到就是我们的 F 可以变成是相减能量的函式嘛，所以 F 能相减能量。那他们是叫什么比例，对不对？那比例 AJ 除以 AL 其实又等于这两个相乘，因为它可以 AKK 消掉。那这个东西又等于是这个，这个东西又等于这个 ，OK？ 那这个它本身又等于 F 的 EJ 减 EL， 所以你就会发现，这两个东西，这三个东西会相等，这左边跟右边会相等啊。那我们再仔细观察一下，如果这个是 X 的话，这是 Y 的话，那加起来不就是前面这个东西吗？所以它其实是 Fx 加 Y 等于 Fx 乘 Fy，所以这个函式会长什么样子？它一定长 exponential 的样子，它会有就是那种 power 的形式，它会有 power 的形式，因为你看它相加就会其实就等于相乘。好，那我们就写 AI 会等于这个东西 EI。好，那一定会有这什么系数，这个系数。那 AI 一定是个正数嘛，对不对？所以 C 一定是正数，这没有问题。那 beta 这边写上去，但是我们会发现 exponential 长相这样子，有点怪怪的。为什么？因为如果你能量太高，你就会有无穷大的 bottle， 这不太合理吧？应该是无穷大的无穷大的能量应该是要越少可能的机会，所以就写一个负的，它就会变这样，然后就可以了。好，那也就是说，越小能量基本上就是越大的几率，蛮合理的哈。好，那所以就是这样。All right, so let's take a look. Alpha I equal to CE exponential minus beta EI. Okay, the number of bottles looks like this. Okay, so now let's reconsider our question. What is the normalized true probability? True probability that your water will be in state I with energy EI. Okay, so now let A be the total number of bottles. Okay, and the probability Pj that a randomly chosen bottle will be in the state J, of course, and is AJ. So of course, we know that if you have energy level EJ, your bottle you have AJ bottles. Okay, so your PJ equal to total bottle or AJ over total bottle. All right, no problem. So the probability is that equal to AJ sum all the A. Okay, so you can see that if we substitute everything here, C exponential minus beta E J and C epsilon K E minus beta E K. Okay, and you delete that. So PJ equal to exponential minus beta EJ over summation of all the E minus beta EK. Okay. So PJ is a normalized probability that, yeah, and randomly choose your energy will be the quantum state J. 这个蛮简单的哈。我们刚刚已经算出我们的 AI 长这样子，或 AJ 啊，哎，随便你啊哈。AJ 那 EJ 的能量是 EJ 这样哈。好，这样子写出来了。我们来问个问题，就是说我们刚刚问的问题是有几个 number of bottle， 对不对？我们现在问，那 how about 我们现在问那真实的几率呢？好，就真实的几率，很简单，它就除以它全部的总量就好了。这就是 A 就是总量，总量怎么弄呢？就把全部的能量的瓶子数量加起来就好了。所以完全一样的事情，只是先C 又被抵消掉了，然后所以我们的几率就是长这个样子，应该没有问题吧？哈，一个是你要看的能量，一个是全部能量加总起来的这种 exponential 的数字。Okay, next one. So now, important. Okay, important. A closed isothermal system, NVT system, contact with a heat reservoir, well, water tank, water cooler at temperature T, no problem. It should be Pj equal to this stuff. We just get this, right? So now we name it 1 over Q exponential minus B epsilon G, B EJ. So this one means Q. We call it Cartesian function. So important. Okay, Cartesian function is everything for statistical thermodynamics. All right, Cartesian function is the core of the most important thing in statistical thermodynamics. All right, again, it can be treated as the sum of all the possible available quantum state. Summation, right? Sum of all the available quantum states. Okay? Right. So, of course, this Q is defined by MV beta. The beta is defined by 10 temperature. All right? Now, I will say beta actually equal to 1 over K Boltzmann constant, KT, Boltzmann constant, K. I will say that, and the unit will be unit is actually the energy of the inverse energy. And we will show this in more detail in the next chapter. Okay, so please just accept that beta equal to 1 over KBT. Okay, but I will show that definitely. Now you accept that beta is actually 1 over KBT. Okay, and QVT. So the Q is a partition function. Partition function is the sum over state, summation from over state, exponential minus EINV divided by KBT. OK， 好，现在我们讲就是刚刚我们算出来这个嘛哈，我们把下面这个东西写成 Q， 这个 Q 呢就是我们鼎鼎有名的 partition function。那这 partition function 之后会常常用到，会常常用到。统计热学就是为了这个，就是从这边开始。那它的意义就是所有可能的状态的总和啊，然后贝塔呢之后我们会讲，它会是1除以 KBT，K 就是那个波兹曼常数 ，OK， 然后unit 它的单位，这个贝塔的单位是 energy 分之一哦，那我们会证明这件事情给大家看下一个章节。好，你看我的文法，中文文法是用英文来讲，哎，真是的。OK， 这听得懂了哈。Next one. So let's take a look of the partition function. What does it behave? So let's see. Is it really the summation of possible states? Let's take a look. For simplicity, let us take the ground state to be non-degenerated, which means that we set the ground state's energy level 0 and no other condition, no other degeneracy. G1 equal to 1 and E1 equal to 0, no problem. So all other state energies are positive, of course. So you can see that 1 plus epsilon I equal to 2 state exponential EI, which is a function of NV, and divide by KBT. Okay, so because we take out especially the first one, ground state, E1 equal to 0, G1 equal to 1. Okay, so you can have 1 in the front, in the beginning, at the beginning. So now let's take a look. If temperature close to 0, Q become 1. Yeah, so which means that when T approach to 0, everything only have one possible state, ground state, Q, 1, Q equal to 1. How about T become infinity? How about T become infinity? Which means that your Q equal to 1 plus T become infinity. So 1 plus 1 plus 1 plus 1, 1, 1, 1, 1, 1, 1. So you can imagine that, which means that if you have temperature high to the infinity, it tells you how many possible states number, okay, total number of states. So it's 1, 1, 1, 1, 1, 1, 1. So somehow together, all the possible number of all the possible states. We have such many, all the possible states. So partition function is effectively measure of the accessible, which means possible number of energy state. 好，现在讲就是 partition function， 我们要看它长什么样，它有什么功用。我们说它是加总嘛，我们来看它这是真的加总所有的状态。我们为了简单化了，我们把第一个状态就说它是 ground state， 它是最基础的，它没有能量，然后它只有一种 degeneracy， 它就是到那边就那边了，没有别的 其他种类。好，那我们把第一项分开来放到前面，这就是一咯。好，那我们接下来看呢，后面当然就从 i 开始，i 到所有的 state，后面写成这样子。那如果今天是零的话 ，t 等于零的话，就 t 趋近于零的话，那其实就是一啦。好，那其他都没了。所以就是说，温度是零的时候，大家都是 ground state。但是如果今天它到无穷大，表示说它可以激发到超大的、超高的能量 state 的话，也没关系。然后它就如果这边是无穷大，你就会发现这后面全部都是每一个 i 都会变成一，表示说全部加上起来就表示说它这个东西到了无穷大，它是到底有多少可能的状态可以被爬到，就对了。所以它是到底有多少可能啦？Q 就是它有多少可能的状态，根据你的温度而改变这样子。So the behavior of partition function, what is behavior? So what is the partition function looks like? So you said it's a partition function, right? We just written down in the previous page, right? KBT, but the probability is exponential minus EI KBT. Okay, so this is the probability, right? Probability. So let's take a look. If the KBT is the temperature is fixed, okay, the temperature is fixed, and if we fix a number that the temperature make the KBT become 200, okay, the 200 you can see that it is Cm minus 1. It looks like a length. It's a little bit weird, right? But we can say this is a wave number. We can call it wave number. It's actually an energy unit. We just said beta is 1 over energy, right? But if we say KBT, beta is 1 over KBT. So the KBT is actually an energy unit. So this is an energy unit. Okay? And we will explain this next page, next chapter. Okay? But we can say that KBT is an energy unit. So this is 200 cm minus 1. This is energy. Okay? And T equal to 300K, and you can say KBT is 200. All right? Now, if a material, well, I don't have time for, well, I need to give you a break, 10 minutes. So I will see you after 10 minutes and continue my lecture. If you have any questions, just come here. Thank you. Welcome back。最近我最近在看，我忽然发现就是看动画的时候，感觉真的是蛮开心的，它可以让我很开心哎。我还发现看动画是一件很开心的事情。嗯，然后就让我最近看的是胆大党，蛮好看的。但我那时候刚开始看漫画，我觉得我没有看漫画，就是我看了第一集、第二集我不想看，但动画真的蛮好看的，然后音乐也很好听。后来我就觉得说，日本的这种创意实在是太强，他们的歌也非常的有创意，就是那动画的歌也非常有创意，然后美术画的都很好，真的是太厉害了。那对啊，就这样，我觉得日本真的很厉害，日本的那种艺术的那种极致，追求极致才是太厉害了，真的很好看。我真的没办法想象，就是不知道啦，我可能没看过美漫，但是我之前有看过一些美漫，就例如说那蝙蝠侠超人那些，我就觉得终究还是跟日本的漫画好像还是有差一点，可能各在座有美国漫画的 fans，那不好意思但这只是个人偏好，但我就觉得好像日本的漫画真的是有它独特的风格，这样，然后从小到大都给我很大的能量，就是让我很开心或者是对，就是而且也让我想很多，就尤其是以前的漫画可能没有，以前漫画就打来打去嘛，但是现在的漫画就越来越有呃深一层的意思，就是如果是小朋友看的话很开心，但是大人看的话就会有更深一层的意思。我不知道有没有推荐给大家，就是那个之前其实前阵子的动画是叫做我不知道叫什么名字，叫什么百分百那灵能吗？还是路人还是什么？就是那个那个路人百分百还是路人100？我不知道大家有没有听过那个？Netflix 上有，就是他就叙述一个人，学生他是有很大的超能力的这样，然后但是他去过得不开心这样，然后他其实蛮深层的意思的，我觉得真的很好看，那可以推荐给大家看。那胆大党的话，目前是觉得说还蛮有趣的，然后音乐很好听，这样。但是路人应该是路人还是超能100，我不知道，反正就是那真的非常好看，跟推荐大家看。然后它的美术音乐都很棒，所以我觉得真的是推荐哦。以前是推荐《进击的巨人》10年前，不好意思，10年前刚加入刚当老师的时候，我跟学生推荐《进击的巨人》，但是他已经结束了，然后现在看也都觉得有点烂尾。呃，但是现在就觉得，路人百分百是非常好看的，对，推荐给大家看。这日本人的创意实在太厉害了。Just recommend some animation, uh like 我不知道英文怎么讲算了，反正 in Netflix some popular animation in Netflix. I really recently it gave me a lot of energy. Good, amuse me, entertain me. Good. Right. So let's continue. So let's talk about if the temperature is 300K and it makes KBT approximately become 200 cm minus 1. Although it looks like an inverse of the length, but actually it's an energy unit. We can call it wave number. And we can explain this later. And then if this temperature encounter to a material or a system with an energy gap so big, like 1000 cm minus 1, or if the second material is 200 energy gap, or 50 energy gaps. We have 3 material. What will it looks like? Okay, so you can imagine that this, for the red material, it is E1, E2, sorry, E3, E2, E1, become 0, become 1000, become 2000. So you can imagine that this is the first gap, and the second gap is so big. So you can imagine that if the red material, so you can take 300K here, and your E1 equal to 0. E1 equal to 0, and this is 200, 200. So you can see that 1 plus 1, 200, this is 0. So it's -1, okay? So if you substitute this E1, 0, 0, and 200 here, and then plot all the values on the figures, and you can see that Q equal to 1 over 1.01, and the first here value is 1, and then in the next 1000 energy level, it suddenly the value drop to here, and 2000 here, 3000 here. So you can see that it is very difficult for a temperature here to reach higher than E2. Okay, so most of the probability is in E1 energy state. But if it is green part, the Q become 1.62, which means that your energy level is 0 and 200, 400, 600. So you can have this value, and you can get 0 here, 0.6, and 200 is about 0.2. So you can see that with the smaller gap, with the same temperature, you can have higher population of atom to jump to a higher energy state. And if the gap is really small, which means that you have even higher chance to go up to the energy level. So this is the first case. If we change another word, we only have the standard material with 200 energy level gap. Okay, again, the KBT still 200. If we substitute this to here, but now we change temperature 30K, 300K, 3000K, which means that if your temperature is so low, which means that you cannot to the next level. So most of the population is still accumulating in the energy level 1, 0 ground state, right? But if you have a higher temperature, 3000K, the Q become 10.9, and then you can see it can go really high energy states, all right? So this kind of makes sense for the material. You see that in the real world. 好，我们要讲的是 partition function 的行为，它怎么样去影响我们的因为它是数学嘛，它用数学怎么样去描述这个事情。那这个当然就是 partition function， 我们前页写到了。那这个上面就是你要的那个 energy level 的分子啊哈。那所以这就是一个叫什么几率，好，这是一个几率值。好，我们要画出这个几率。好，首先呢 ，KBT temperature 如果是300K 给你的话，那 KBT 就约等于200。 那这个200这个 cm-1 其实它是一个能量的单位哦，好，能量的单位。那之后会讲。那我们刚刚不是讲 beta 等于1/kBt 吗？那它是 energy level 的energy 的 inverse 嘛，对不对？哈，那这边 kBt 当然就是能量单位。好，我们现在来检查3种材料，一种是 energy gap 超大的，一种是200的，一种是超小的50。那每一个会怎么样呢？我们来带进去看看，就是我们如果有很多 energy，OK，energy level 0、1000、2000、3000、4000这样，这是大的 energy level。好，那这个东西我们来看，如果今天我们把它这个带入这里，然后我们看第一个 energy level 带到上面，我们就会发现它的 Q 大概等于1.01，然后它如果是1带到分子的话，它几乎就是1了。那但是到 energy level 1 1000的带到这里，几乎就没有了，就没有了。那等于是说你的 energy 的 gap 超大，你这300K 根本没办法让很多原子爬上去，还是有哦，这不是为零，还不是为零哦，但是它基本上就是很少很少很少了。那如果今天是200的话，它就会变比较多，然后更小的 gap 的话，它就会爬到更高。所以跟材料就是不同材料的能阶，它会有不同的现象。那如果反过来讲，如果你的同一个材料，它就只看同一个材料是200的那个 gap，那如果你的温度30K 跟3000K，你会得到不同的 kBt，然后你会有不同的这个值带进去。如果今天你只有30K 的话，你就大部分的 particle 都会在 ground state 等着，然后只有一点点会被激发出去，而且它是非常少的几率的。那如果是300K 的话，就是这一条线；如果3000K 的话，哇，大家都跑到很高的能阶上，所以这其实是蛮符合我们材料的现象的。Okay, next one. So Boltzmann population function is what we talked about. It's T. Okay, this is what we talked about. And then if we have the P, everything becomes easier to connect to macro state property. For example, E bar is the expected value times its probability, summing up together. All right. So this is really useful. And you see, the most useful formulation in all of the statistical thermodynamics, right? Boltzmann distribution, or we call that canonical distribution. All right. And the above equation can be derived directly from S equal to KB natural log W. Okay, this function is a bridge between classical and statistical thermodynamics. This is a bridge, very useful. 好，那就波兹曼population 叫做人口密集度嘛，哈，这种感觉哦。那当然这个不是人口了，它变成是 atom 的能阶的占据的密集度，这就是我们刚刚画的这张图啊。那它就是 P， 然后上面就是你要的那个，你要看哪一个能阶的几率嘛，哈，它就是主角，然后这是全部，就这样。然后呢，有了这个东西就很好用，因为你只要有它的能阶的值，还有它自己的几率，每一个几率每一个能阶全部加上起来，就是它的期望值。那这个期望值就是你现实生活中看到的这个，通常它就会跟你现实生活中看到的能量是一样的。OK， 好，然后接下来它非常有用，然后它要么叫做 Boltzmann distribution， 要么叫做 canonical distribution， 啊，就是名字的问题。然后呢，这个可以直接跟 S 等于 KB natural log W 这个式子连接，哦，超重要的，因为这个式子就是连接传统跟统计热力学之间的重要桥梁。OK, next. This page is really, really important. Okay, we call that Q and Z. In the textbook, the partition function is Z. Okay, but why I gave you Q? Because personally, I found that textbook Z partition function has really, I don't know what it, I don't quite like the explanation for Z in the textbook. So I just try to find other way to tell you what is Q is, and then correlate Q and Z for you. All right. So I choose a different route, different path. Okay. So now you know Q, right? The probability that member of the ensemble in quantum state J is EJ. This is what you know, right? So the EJ here is ensemble energy. Ensemble energy. But in textbook, the textbook is their formulation is epsilon. Epsilon is actually the molecular energy. So you can see that they are really similar. Okay, they are really similar in the sense of the physics. You see, this is the water bottle, right? But now you can say the probability that a molecular is in molecular energy level. So you can treat that the energy is actually the molecular energy state. So you can see that they looks exactly the same, but this one is the ensemble energy. But now if we talk about molecular, it's epsilon. Just changing the thing and the symbol, right? So this is the same. Okay. Then textbook Z here is a little bit different from the ensemble energy summation, because the partition function can be written as summation over state, right? This is what we learn. We learn that from states, right? State. But in the textbook, they sum it out through levels, energy levels. Okay? So you can imagine that the figure here. This is the state. We have many states. We have many states. Okay? But maybe, but we have energy level. Energy level. 1, 2, 3, 4. So what's the difference? If we sum them through the state, which means that we sum them here, sum them all together. But if we, but in the textbook, they said they sum through the level. Level 1, level 2, level 3, level 4. But we need to consider degeneracy as well. G. So you see the state and level very similar. What? It is energy level times Gj. So you see, you sum through a level, you need to times 4. Become a state. So this is Gj. G1 maybe. And you need to multiply their degeneracy. So actually they are the same. This is sum through states, but this is sum through levels. But if you sum through levels, you need to consider degeneracy. All right. So represent the degeneracy level are written once and multiplied by Gj. Yeah. Okay. So Q and Z actually, if you understand Q, you can understand Z. The only difference is that their expression is different. The first one is ensemble energy become molecular energy. The other is they in textbook they sum through level, but you need to consider degeneracy. But if you using the if you follow what I taught in the previous hour, we sum through the ensemble energy and we sum through the state, but actually their concepts are exactly the same. Okay, that's it. 好，这一个页啊，蛮重要的，就是课本上的 Z， 我觉得他讲的非常不清楚，然后你们拿来写什么哈，所以我就去上网找别的教材，然后我觉得这样比较好懂 ，Canonical Ensemble 的比较好懂。那我们就像刚刚这样教完各位以后，再把 Q partition function 连接到课本当中 Z 的 partition function， 你会发现它上面写的是 epsilon， 那这个 E 跟 epsilon 其实一个是 ensemble energy， 一个是 molecular energy， 其实就是你的 focus 是不一样的，一个是瓶子，一个是 molecular， 就这样。然后呢，接下来 Z 它写成 Z 是什么意思呢？它其实 Z 跟我们的 Q 是很像的，只是它课本上是从 energy level 上去加，它的 summation 是从 energy level 去加，但是它要多乘一个 GJ， 那其实跟我们不是一样嘛？我们加 state， 我们是加这个 state， 那实际上跟我们加一个 level 然后乘上4，跟加一个 level 乘上2啊，不是一样吗？好，所以这两件其实都几乎是完全类似的。OK， 所以说如果你懂 Q 的话，其实课本上的 QZ，课本上的 Z， 我们的 Q 是意义是一样的，它也是 sum over state 哦，它也是一样，只是它就 level 的方式跟 molecular 的方式来看这件事情。Okay, so if you can understand this, good. Then let's connecting classical and thermodynamic, classical and statistical thermodynamics by using the S equal to A natural log W. Okay, and this is so famous and carved on the Boltzmann's tomb. Okay, this is so important. And so toward the equilibrium state, entropy S will increase, right? And we said, you can see that the S is a function of W. The W is thermodynamic probability. So you can imagine that the FW is a single value that monotonically increasing function. What does that mean? Which means that it will always increase. It will never go down. Okay, you won't see this curve here because it's really difficult for us drop and then go. So this S is a function of W. Okay, and so you can say the entropy will increase when the W has more possibility, more choice to do that, right? And then, for example, now Boltzmann said if you have system A and system B, the SA equal to FWA, SB equal to FWB, so the total will be SA plus SB, very similar to the water cooler things that we just explained. So FW total is FWA plus FWB, but because their probability, thermodynamic probability should be independent, right? Independent. probability. Probabilities are multiplicative, which means that if two thermodynamic probability summoned up together, actually their probability need to be times together because their choice double. I mean, not double means that if you have WA choice, if you have WB choice, and you sum it together, your choice become multiplied, right? So FWA, FWB. Again, if something is plus become multiplication, the F must be natural log W with a coefficient. So that's how Boltzmann showed this important equations. OK， 好，那我们现在就要解释这个 S 等于 K natural log W。那我们就博兹曼就是觉得说 ，OK， 这 S 其实跟它的选择是有关系的。那而且他观察这 S， 它其实是就是1对1 W 对一个 W 对一个 S， 然后它就是往上涨的，不会是往下跌的这种 monotonic， 就是一路往上的那种感觉的 function。好，然后 system A 是长这样 ，system B 长这样，那 total 的话就是加起来，那也就是 FWA 加 FWB。但是呢，如果是以选择状况来讲的话，高中的时候我们都知道，如果今天你选择忽然变多了，那你的选择就会是相乘的，而不是相加的，对不对？哈，所以呢，所以它的 FWA 乘上 WB 其实是会相等于 FWA 加 FWB。好，那这样子算法，我们就发现，那这个 function 一定会等于它长得很像 natural log。那这个 natural log W， 那当然还会有一个系数在前面，就变成这样子了。OK， 所以说就是用这样子的方式把 entropy 跟选择的方式串在一起，就从这边你就可以把等一下很多统计的跟一般的热力学、传统热力学连在一起。好 ，next really quick entropy how to increase that? Y natural log it's given S proportional to NW, which means that S is an extensive properties. Okay, so it's proportional to the mass. Okay, so the extensive properties. So you can see that if you have more mass, more stuff in the system, which means you have more choices, right? So more choices, which means that if you want to increase in entropy, you add a particle, okay, and you add energy, increase the entropy, and you increase the volume, and you decompose molecules. If you decompose molecules, you have more choices. And if your polymer bended, which means that you have more degree of freedom. So yeah, just make it more random. Okay, more choices means more random means more choices. So you increase the entropies. Right. And if you previously you sum and now if you minus, you become factorial. It's okay. Ratio is okay. So disorder is a type of driving force to kind of because increasing the S is material want to toward increase S, right? Increase S. So disorder is also a type of driving force to make it higher entropy. 好，其实这很快，大家都已经尝试了哈。那之前都知道 entropy 就是大家想要越来越大，然后越 random。那其实大家如果可以理解这件事情的话，其实跟我们的 statistical 就非常有相关，因为你越 random，你就越多选择。好，这边都是越多选择的方法。例如说加 particle，那当然就越多选择啊。你加能量，当然越多选择啊。本来不能到的 energy level，你到达了，就可以到达，所以你就可以更多的选择。那你更多的体积，你就当然有更多的自由度。你有原本是合在一起，你把它 decompose 你就有更多的选择啊，因为不同的状态啊，就有更多不同的状态的感觉。那你原本只是平平的一个，它当然是会希望说越多选择越好，它就可以扭来扭去，它就会有更多的选择。所以说 entropy 这件事情就是，而且在 classical 那时候我们也讲到 entropy 其实它就是我们会越来越想要让 S 更高，那 S 更高，它等于是说它会自动会往那边走，它其实这种 driving force，S 会往那边走。那越高的 S 不就是越 disorder 吗？所以你也可以说 disorder 想要变成 disorder 也是一个 driving force，就这样。Now we're actually going to use quantum mechanics things. Okay, quantum mechanics things. Quantum mechanics is originated by the Blois ideas, which is P equal to h over lambda. So they found that actually a light previously they think light is a wave, but the Blois found that actually it has particle behavior because they use light and hit the metal plate. Metal plate. Metal plate. And then it found that there's a particle jump up because the light hit. So they think the particle of the light has particle behavior, which has momentum. Because if they don't have momentum, they won't kick out particle out of the metal plates. So it must has a momentum. So the momentum is correlated with h divided by lambda. Lambda is the wave length. So you can see that higher longer wavelength has lower momentum of the particles. Okay, so Nobel Prize get that, and it's quite handsome. Winner. OK， 好，就讲说我们开始要借用量子力学。这位帅哥的布罗利他发现他做了一个实验，之前都是 light 光，他觉得是波，结果光打到金属板上，竟然会有东西跑出来，也就是说它已经被撞到东西了。那就好像是你打一个颗粒到它上面，所以说他觉得光也可以有粒子的行为。那什么意思呢？就是光波也有粒子的行为呢？他就是说他写了一个式子，就写 T 等于它一定是有一个 momentum 去撞到 metal plate， 它才会有东西跳出来嘛，所以他就把它写出来 ，P 等于 h 除以lambda，然后就得到诺贝尔奖了，真厉害。And then also another thing is that another mechanical. So first thing is that first thing we need to know is that light particle may has wave behavior. Wave behavior may have particle behavior. Okay, so they actually can be mixed up. Okay, so the next things of the quantum mechanics is that a particle in the box. So you can imagine that there's a box, and if you do the observation, particle bouncing between a wall, dun, 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 dun. We expect if you take a photo, and then overlap all these figures together, you can see that actually it looks similar density, right? But it's not. The density is higher in the middle. So when you see the bouncing particle, one box particle in a box bouncing between the wall, actually you observe more in the middle. But we thought that it should has equal uniform density, right? So this is weird. And if we make it higher speed, you have higher chance observed in this particle in two positions. And if you have three, even higher energy, you have higher possibility in three positions. So the particle behave like a wave. Okay, this is a higher possibility to observe that. Really interesting. Okay, so we can describe the particle velocity in terms of the Broglie equation because it behaves like a wave. OK， 好，这时候刚刚我们讲到就是另外一件事情，就是如果今天有个 particle 在箱子里面跑来跑去，左跑右跑，左跑右跑，一维的哈，左跑右跑，我们预期它应该是，如果你每次一直照相，你会发现它可能在这里，它可能在这里，它可能在这里，它可能在这里。我们预期它会一样的几率，就其实不是哎，它其实中间比较高几率哎。那如果你更加高的它的能量的话，它几率高的是在这两处，然后再更高的话变成3处，那就这跟我们想象不太一样，所以实际上它是以波的方式在里面弹跳的，它跑来跑去的，所以呢，我们要以波的方式去看这种超微小的东西的行为，就要使用刚刚我们介绍的 de Broglie 的 equation。Okay. So now quantum mechanics and waves. So again, we know that the particle bouncing in the box is following the wave behavior. So let's consider the wave behavior here. So now, if your length of the wall is L, okay, so there are several energy states that you can have. For example, the lowest energy level is that only one high possibility zone. So which means that this is anti-node of this wave. Okay, so you can see that this anti-node of wave is what is the length of the wavelength? Actually, it is here. This is lambda 1 is 2L. It's only have it is the L is only half of the wavelength. Okay, and how about high one level higher? Okay, this is lambda 2 equal to L. If you have even higher length, higher energy level, your lambda 3 equal to 1/3 2L. Okay, so you can see that lambda J equal to 1/nj 2L. So you see this length is relative to the L, and also nj is the number of anti-node. For example, lambda 1, n1. okay, is 1 because you only have one antinode. So lambda 1 equal to 2L, lambda 2 equal to L, lambda 3 over 1 over 3 2L. So your lambda wavelength lambda equal to 1 over nj times 2L. Nj is number of antinode. 1, 2, 3. Antinode A lah. Node is something that you typically won't vibrate. Okay, so lambda j can be written here. 好，接下来讲的是量子力学跟 wave 啊，跟波。那刚刚讲到波啊，哈，就是第一个等级的波就是这样子，喵喵喵喵，这样上弹下弹上弹下弹这样子。那这样子的波长其实是才一半而已哦，所以你的长度的 L 其实是2倍的长度 L 才是你的波长哦。那如果今天是下一等级的话，就是雕这样子，那正好它就等于它的波长 L。那如果今天再下一个等级，就变是又是这样子，所以是1/3乘上 2L。所以呢，我们可以归纳出一个公式，就是浪打 J 会是1除以 NJ 乘上2L。这个 NJ 是什么呢？就是它的节点呐，哈，就是最高点 A 有几个，就是这样子算出来就可以得到这个式。OK，next one， Schrödinger equation。Schrödinger equation, I don't know, does not pronounce it. Okay, anyway, but P equal to H over lambda. You understand this? And again, this is one dimensional, right? Because we talk about the particle in the box bouncing between left and right. Okay, so your Px, momentum P. Momentum Px equal to Nx H divided by 2L. You see, lambda, right? Lambda is 1 over Nx times 2L. So your lambda is 1, this one, okay? And the H is H. So this is one direction. In 3-dimensional. And of course, you know there will be Py and Pz. Okay? So it becomes 3-dimensional. Particle in the 3-dimensional box here. So for rectangular coordinate system, Px, Nx, H2L, no problem, right? Py, Ny, H2 over H over 2L. Pz, Nz, H over 2L. Okay? So you can imagine that momentum vector sum. Momentum vector sum is that if you have 3-dimensional, you can represent it as a vector. So Pj2 equal to Px2, Py2, Pz2 square, sum square, and then sum out together. And then because they are all the same, so you can take up and you can say this one, Nx square, Ny square, Nz square, summing out together. And then, because this is a little bit ugly, can I written down here Nj square H squared divided by 4L2, and where Mj square equal to Nx squared plus Ny squared plus Nz squared. Just make it easier for us to understand. So if you can understand this, we say n, x, n, y, and z are integers because integer is anti-node number, right? So it's their integer. Then we call that quantum number. All right. Later we'll use quantum number to define their energy states. Okay, and then 讲完了啊，就是说我们现在确定嘛哈 ，particle 有 wave 的行为啊，然后我们就必须要使用波长，然后我们波长把刚刚算出来的波长带进去，因为我们现在只有讲一维嘛哈，所以 px 是长这样子，那一定有 py 跟 pz 啊，所以各分别写出来。那 py、pz 跟 x 它们都是单一轴，所以我们要把它写成向量的状态的话，我们就把它平方相加起来，我们就可以有。好，那 n 这个东西它都是波的峰值嘛，对啊，有几个峰值，那它一定是正整数啊，所以它就会变成是要么就是1，要么就是2、3、4，所以我们叫它 quantum number。这些东西就会让我们去决定它的能量状态。OK， 等下就会用到了。All right, so as we say, the Nj, N1, N2, N3 is the value that we can specify the energy. So we can see that the kinetic energy of epsilon of a particle is half mv squared, no problem. And the momentum is mv, right? So this is mv. So if we square them and divide by 2m, so you can get half mv squared. So your kinetic energy actually momentum squared divided by 2m, no problem. So the kinetic energy of J level is that Pj squared divided by 2m. So we use that Mj squared divided by h squared 8 ml squared Mj squared h squared divided by 8m. Okay, so L squared. You can imagine that volume equal to L cube, right? So you can replace L by V divided by -2/3. So now you can see that the epsilon J is proportional to V times V to -2/3. Of course, it also proportional to the Nj. And you can see that if the V becomes smaller, your kinetic energy will become higher. Okay, and then the Nx, Ny, Nz can define the energy. So your Nx, Ny, Nz can be 1, 1, 1, can be 1, 2, 1, can be 1, 2, 2, 2, 2, 2. So there are many possibilities for this, but we don't have time for today. So next week we don't have lecture. I will upload the video. Suppose, and I will give you a vote for next week. Should I do the presentation here or I upload video? Okay, so if you have any questions, just come here. Thank you very much. See you. Hopefully see you next week. Okay, bye bye.
看这边这个就是摇头，因为它都是sample，然后这边就是这个是 ensemble，然后这边是 molecule，就是这两个是
哦，没有，这边是thermal energy，对，thermal energy，
对，
一样的意义。
哦，
好，然后如果这边你可以通的话，那我们要解释 z 跟z，其实q 就是这样子嘛，
对，
只是这边是thermal energy。那我们现在可以，那如果你 q 了解的话，那 z 其实一样东西。就是你 z 可以是 sum through the state， 也可以 sum through level。
哦，
是这样的意思。
对，
对，
我以为是这边跟这边比较，
不是，是意义问题。
哦，好，谢谢。
谢谢。